When the input signal is large enough that the diode operates in multiple regions, we use large signal analysis. In this video, I will develop the approach that allows us to determine the output of a circuit with a diode given a large, time-variant signal on the input. I will start with a simple, but very common circuit known as a half-wave rectifier. This circuit is part of many power supplies. The next videos will use the approach developed here on more complicated circuits. Let's begin. We are trying to relate the input to the output. I know how the story ends, so allow me to cheat and adjust the scale of the plot. We can develop the relationship graphically, or as a piecewise function. We call either of the forms transfer characteristics. This one is a relationship between two voltages, so we call it a voltage transfer characteristic. But you may run into problems where this is not the case, so we'll keep the more general term. This analysis assumes that the signal is of low enough frequency that we can ignore any reactive components. There is a lot of information in either of these representations. That means we will do a lot of analysis to develop them. We need to find the input value, that is the border between the reverse and forward regions. We need to find the input value, that is the border between the reverse and breakdown regions. We need to find the relationship between the input and output for each of the three diode regions. Breakdown, reverse, and forward. There are some intermediate values we will find along the way, but I think it is best to introduce these as we need them. So let's get started. Let's take a waveform we are likely to find in a power supply, a 24-volt sine wave at 50 Hz. First, apologies to the part of the world that uses 60 Hz. The round numbers looked better on the axis. Second, the 24 volts is a typical value after voltage is stepped down by a transformer. The circuit is the simplest first step to transforming the AC signal to a DC signal. First, we will assume the diode is in the reverse region, and find an expression for the diode voltage as a function of the input. I will continue to abuse nodal analysis, as it will scale well to future circuits, including those with transistors. For this circuit, we only need a single KVL and a single KCL. These will give us the node voltages, and we can add a KVL around the diode to solve for the expression we are trying to find. Through all of these, I leave the input as a symbolic variable, since we are going to let it take on many values. I do the same thing in MATLAB as I solve for the expression of the diode voltage. We use the output of this code as the expression for the diode voltage as a function of the input. This expression leads us to find the two values of input that move the diode out of the reverse region. If the voltage across the diode is in the neighborhood of 0.7 volts, assuming the diode is silicon, we know that the diode is switching on. Setting the diode voltage expression equal to that 0.7 volts and solving for the input gives us the value we are looking for. Doesn't this feel silly for such a simple circuit? It won't with more complicated circuits, I promise. Now we do the same thing to find the input value that moves the diode from the reverse region to the breakdown region. For this, we need to know the breakdown voltage. This value will vary with different diode models. What won't vary is that the value is specified as a positive value, even though it should be a negative value. If we are keeping the diode VI plot shape in our minds, this breakdown voltage is in the left-hand plane. The specified breakdown voltage is the magnitude of the reverse voltage. If you keep your signs consistent as I have, it'll be negative. These values are not tightly specified for diodes that are not Zehners. Let's use 75 volts. setting the diode voltage expression equal to that negative 75 volts and solving for the input gives us the value we are looking for. Let's tuck away the input signal for later and start to build the transfer characteristic. The reverse forward border belongs here. The reverse breakdown border belongs here. Now we need to find expressions for the output in each domain. We already have the analysis done for the reverse region, so let's start there. For this circuit, the output voltage is just the voltage across the resistor. We can get this out of MATLAB, a bit silly here, but it will serve us well for more complicated circuits. Here is the code I used to find everything we've needed so far: the diode voltage, the border values of the diode regions, and the circuit output, all in terms of the input voltage. And here is the output of the code. All of this analysis assumed the diode is operating in the reverse region. We can then add the output expression to the plot, but only in the reverse domain. Now we've extracted everything we need from the reverse assumption. Let's move on to the other two assumptions, starting with the forward assumption. If the diode is silicon, the forward assumption leads to a drop of 0.7 volts. For this circuit, we write two KVLs, first for the voltage supply and a KVL for the diode. The output is still the voltage across the resistor. I'll show the MATLAB and its output again for the sake of consistency, but we could probably work this one out on paper. We complete the expression for the output as a function of the input using the result from this code. We can add this expression to the forward region of the transfer characteristic. Almost there. The last domain is filled in by assuming the diode is in breakdown. We'll use the breakdown voltage for this assumption. I enjoy this one because the analysis is identical to the forward assumption, simply with the different assumed diode voltage. I'll abuse MATLAB once again. Don't worry, it deserves it. The result from the code allows us to complete the expression for the output as a function of the input for the breakdown region. We add this expression to the breakdown region of the transfer characteristic. This is a complete representation of the relationship between the input and output of the circuit. Now let's bring back that input signal. The borders on the transfer characteristic that are vertical correspond to borders on the input signal that are horizontal. Notice the borders on each plot correspond to values of the input voltage. We can see that the input signal crosses from the forward to the reverse region, but never into the breakdown region. So let's make some room by removing that border. Let's also zoom in on the transfer characteristic to match the range of the input signal. We can now start the process of mapping the input signal to the output signal by passing it through the transfer characteristic. The input is the horizontal position on the transfer characteristic, and the output is the vertical position on the transfer characteristic. As we move along the horizontal of the transfer characteristic, according to the input, we trace the output along the vertical of the transfer characteristic. Since the input and output have the same unit, you may find them plotted on the same axis. Let's take a closer look at the two waveforms. The half-wave rectifier circuit in this analysis removes the negative half of the waveform, a first step to converting an AC signal to DC. But the positive half of the waveform is also affected. Notice the input and output are not identical when positive. The output is 0.7 volts less than the input because of the drop across the forward bias diode. The input has a peak value of 24 volts, while the output has a peak value of 23.3 volts. I'll record one more example of large signal analysis with a more complicated diode circuit, and then move on to small signal analysis. So stay tuned and good luck.